Hello, welcome to my video presentation for the DSP module. So we'll start straight away with the checklist. Firstly being to make a recording and import it into MATLAB, play it back, and also store the sampling frequency of that recording into a variable called fs. So we'll do those together because first step to importing it is to let IP and fs equal to audio read function of my recorded file, which I've saved onto my desktop earlier on. That's just path.wave. Now you'll notice that IP is a double column vector, so we'll just tidy that up real quick with IP equals IP colon comma 1. Great. Last thing to do then is to just play the signal back. So to do that, I'll just do sounds IP comma fs.
Patrick Ostapchuk.
Next, we're going to plot the speech in the time domain with the x-axis being time in seconds. So we'll set up our x-axis t, which is 0 to the length of the input signal IP minus 1. And that's all divided by sampling frequency fx. Then we'll do plus t against IP. And there it is there, and we'll just throw on the x and y labels. So the x-axis is time in seconds, and the y label is amplitude. Lovely, and that's the plot there. Right, so next we have to run some given code that was in the checklist, and it just returns two variables, which is tone frequency and noise cutoff. The next step then is to synthesize high frequency noise and tone and add them to our speech signal IP. So we'll make the tone first because that's a little easier to make. So tone equals 0.1 times cos, and this is in radians, so we'll do 2 by pi times our tone frequency times t. And as for the high frequency noise, what we do is we use the random function to just get random signals at random frequencies, and using a high pass filter we can get rid of the low frequencies, leaving us with just high frequency noise. So how we do that is we let noise equal to random of size IP, and we'll also create our high pass butter filter. So BA equals butter. We'll do high enough order for a good roll off, so B6, and that'll be the noise cutoff over the Nyquist frequency, or fs over 2, to normalize it. And that is a high pass filter. Now we'll just put the noise through our new filter. So noise equals filter of BA noise. Great, so that's our tone and noise created. And now we just have to add that together with the input speech to make a new signal. You'll notice here that the tone is one row and a whole bunch of columns, whereas the input speech and the noise is a bunch of columns and one row. Yeah, that's right. No, sorry. That is one row and a bunch of columns. And this is a bunch of rows and one column. So what we have to do is transpose the tone. So signal equals tone transposed plus noise plus IP. So I'll just show you what that looks like then in the frequency domain. So to do that, we'll plot ABS of FFT of tone. Yeah, nice. We'll use to hold on and plot the same thing, but with, what was it, the noise. And also we'll do the same thing with IP. Oh, so that's our three components there, and what I'll do now is plot just the signal in the frequency domain, and hopefully it should look exactly like this, but just in one color. And plot yes FT of signal. And there we go. So this would be our speech, this is the tone we created, and this is the high frequency noise. Now, next up, we have to design a second order filter using MATLAB's butter function with the cutoff frequency set equal to half the noise cutoff frequency. Right, so we'll just use the butter function again then. So B and A equal butter, and it was meant to be a second order filter with noise cutoff over 2, and that's all over the Nyquist frequency again. And we'll make that a low pass filter. Good, and that's the second order filter made then. Our next step is to draw a signal flow diagram and make its difference equation. And we'll also have to calculate by hand the first three outputs using what we've done by hand. So before I move over to pen and paper, I'm just going to note down a few values we're going to need. The first one being our B coefficients, our A coefficients, and the first three inputs, signal 1 to 3. Great. Right, so I changed my mind a little bit. We'll do this on just paint. So first thing I'll do is draw a signal flow diagram using the B and A coefficients. So we've got our input x of n, isn't it? Yeah. That goes through 3 B's. And as for the A coefficients, go through 2. D, D, rats. Again. Great, so I'll just put in my values then. So this is my first B, 0.2299. My second B, 0.4598. And my third B, 0.2299 again. And these are my A coefficients minus 0.2643, and my other a 0.1839. And the output then, of course, is y of n. Now let's write out the difference equation with the b and a coefficients. And that comes out to be y of n equals 0.2299 times x of n plus 0.4598 times x of n minus 1 plus 0.2299 times x of n minus 2. And then we bring our a coefficients as well, so this will be plus 0.2643 y times y of n minus 1 minus 0.1839 times y of n minus 2. Great. Last but not least then, we have to calculate the first three outputs for y of n. So we'll start with getting out y of 1. Let me move this down a bit. So y of 1 equals 0.2299 times x of 1, which is 0.1001, 01 times 0 basically. Yeah, so the other two x terms in this go to 0 because there's no known value for them, is the way I'd put it. And there's also no y values, so y of 1 is just this first term here. So hopefully it doesn't look like I'm pulling numbers out of thin air. I've got a calculator on the side here. So the first answer then comes out to 0.02301. Now next we'll calculate y of 2. And y of 2 is 0.2299 times x of 2, which is this value here, 0.0944. 0944 plus 0.4598 times x of 1, 0.1001. This term will go to 0, the x of n minus 2, and that is plus 0.2643 times y of n minus 1, and we just solved that earlier, that's 0.02301. And the final term will still drop down to 0 then. And when we multiply that out on the calculator, we get 22909 plus 0.2643 times 0.0301. We get 0.07381. Now, the final term then, y of 3. Right, so again, it's 0.2299 times x of 3, which is 0.0828 plus 0.4598 times x of n minus 1, which is 0.0944. And that's plus 0.2299 times x of n minus 2, which is 0.1001, plus 0.2643 times y of n minus 1, which is 0.07381, minus 0.183839 times y of n minus 2, this value up here, 0.02301. Now, just be a second, plug all that in the calculator. 0.2299, 28, 0.4598 times 0.944, 299 times 0.101, plus 0.2643 times 0.07381 minus 0.1839 times 0.02301. And our answer for that is 0.1007. Now, I'll bring these three outputs then back into MATLAB, where I'll compare these results using code. Right, so we're going to verify our hand calculations with MATLAB code. So earlier on we got B and A coefficients, and what we'll do is let y equal a filter using our B and A coefficients and our input signal. And we'll just ask MATLAB to output outputs 1 to 3. So these are our three outputs, and let's compare that to what we did by hand. 0.023, 0738, and 1007. These three here. And those match up nicely with what we did with the filter function. Right, so the next step is to design a minimum order filter which will reduce the high frequency noise by at least 60 decibels with a maximum of 3 decibels ripple allowed in the passband. And the passband is 0 Hz to fs over 4 Hz. For normalized terms, it's from 0 to 0.5. So first we'll use the but_ord function to get a cutoff frequency and the order of the filter for n and omega. And that will equal to but_ords of everything given to us in the question, really. So right, that was from 0 to 0.5, so we'll do 0.5 as the pass band. Stop band will be the high frequency noise, so noise cutoff, and we'll normalize that with fs over 2. Pass ripple was 3 decibels and the stop was 60. That gives us n and w then, and we'll let our new B and A coefficients then equal butter times order of the filter, comma, cutoff frequency. Great. Next up then, we have to design a second filter to reduce the tone by at least 40 decibels and make sure that the system is stable. So to do that, we'll set up new B and A coefficients, B1 and A1, and let those equal to the stop band order function, and we'll try with a high order and hopefully it'll work. So we'll do like an order 10, and the frequencies is the frequency of the tone, and we'll just give it a range of plus or minus 50. So that's tone frequency minus 50 and tone frequency plus 50. And as we're doing with everything, normalize that as well. And that needs to be a stop. So just to verify if the system is stable or not, we'll put the B&A coefficients through the z-plane function so we can take a look at it and see if they're in the unit circle or not. Yikes. So no, they're not is the short answer. So let's bring the order of the filter right down. We'll see if 4 will give us what we're looking for. Zoom into that. We're just shy of making the system stable. So let's just make this maybe 3 instead. Right, I call that stable. The zeros are on the unit circle and the poles are within the unit circle. In other words, our second order filter is stable. Or sorry, our second filter, the stop band filter, is stable. Right, the next stage then is to apply both filters to the combined signal, which we made earlier. It was the input signal plus the noise plus the tone we made. And when we apply those filters, we need to plot the magnitude frequency content of the input and output in hertz, and also label the axis. So we'll take our B&A coefficients we made first for the high frequency noise filter. So y equals filter of B, A, and combined signal, and y1 equals the filter for the tone we made, the stop band filter, B1, A1, and y. Now, I'll just set up the frequency axis first in hertz. So frequency axis is equal to 0 to the length of the input signal minus 1 all over the length of the input signal, and that is multiplied by sampling frequency fs. And now we can plot the input signal against the filtered signal. So I'll plot frequency axis against ABS FFT of signal. And I'll hold on to compare that to the filtered signal, Y1. Great, so that's the filtered signal, and I'll just slap on some labels to that. So the Y label is magnitude, and the X label is hertz. Oh, frequency in hertz. Last item on the checklist is to identify a low frequency component that will produce a significant phase shift in the first filter and pass a sinusoid of that frequency through the filter. And we have to verify that the phase of the tone has been altered by the expected amount. Right, so first of all, I'll hold off on previous plots, and we'll just take a look at the freq Z of B and A. And just another quick thing we'll do is improve the resolution by sticking in 10,000 here, just so it's a bit easier for us to work with. And we'll look for around minus 45 degrees. Right, there we go. So To get the frequency of the tone we need to multiply this x value by the Nyquist frequency, which we'll do while we create the tone. In other words, tone 2 equals cos of 2 pi, to make it in radians, times Nyquist frequency fs over 2 times our x value that we picked, which was 0.1667, and that is by t. Now we'll pass this tone through our previous filter and compare the phase shift in them. So y2 equals filter b comma a comma tone 2, and plotting them against each other, plot tone 2, hold on, plot y2. So that's our output signal there. And let's just take a look at the phase shift between them. Right, so you can see that the output y2, the one in orange, is about 1/8 out of phase with the blue input. So we can say that there's about a 45-degree phase shift in the signal.